Hey folks, welcome back to our series on Vertex Operator Algebras. In today's episode, we'll study the action of the Virasoro Algebra on the Heisenberg modules that we've been investigating lately. So let's start with a bit of a review. Let H be an abelian Lie algebra, from which we can define the untwisted affine algebra H hat as the product of H with the Laurent polynomials centrally extended. Note that because H is abelian, the only non-vanishing bracket occurs here. Clearly, this algebra has a triangular decomposition, and also let's recall that we can append the degree derivation of the Laurent polynomials. Since H is abelian, we can employ the simple involution omega equal to -1 on H and extend it as usual to Virgulilla H, with the usual half z grading involution included, affording a twisted construction of both H hat and Virgulilla H. We can now define the Heisenberg algebras as the commutator subalgebras of these beasts, which we now simply refer to as H hat z for short. The symmetric tensor algebra over H hat z minus, the negatively graded subspace, are natural modules for H hat, which can be thought of as the space of polynomials in negative degree monomial basis terms. What we're interested in today is the observation that this module admits an action of the full extended affine Lie algebra. Now, let the generic elements like x times t to the m be represented by operators x of m in the module s z hat minus. It's pretty clear that this representation affords this simple representation here, where the central charge c is now implicitly the identity operator. D again acts as the degree operator, as you might expect. So now we want to build the operators akin to those of the Virasoro algebra dm on the s of z hat minus module, which we should expect to exist given that the Laurent polynomials are present as a factor in the algebra. To that end, recall that there's a canonical choice of quadratic form on the tensor product T2 of H, which we'll call omega 0 or whatever, with Hi providing an orthonormal basis for H. FLM makes the note that we can always assume that such a basis does exist, for if it doesn't, we can extend the field F to create one that does. Now, we can use this canonical quadratic form to form the backbone of the operators L of m, which are just products of operators of degree m minus k and k. Note specifically here we have non-zero m. For the operator L of 0, we have to be a little bit more explicit to ensure that it's well defined. This explicitness has the cost that we have modeled as a scalar times the dimension of H. This requirement exists because the two operators here, hk and h of minus k, don't commute, and there's no canonical way to order them. Nor is there kind of a canonical way to choose a path through z. So our adjustment here, the constant term, amounts to specifying a path through z and therefore an associated ordering of these operators. Okay, with the operators built, the hard work remains. We now claim that L of m forms a representation of the Virasoro algebra, and in particular, we wish to show that the central charge is given by the dimension of H. But that's all for today. We will prove this claim next time.